Julia. Okay.
Yeah, that's right. It's yeah, I forgot his name.
Viral.
Yeah. He's from Stanford, I guess. Stanford or some university. Actually, he moved from
University of California.
Yeah, it's not Stanford. Sorry, UCB, University of California.
He was actively involved in Aadhaar project,
Oh, okay, interesting.
and he is rebooting India. He has written a book with Nandan
Nilekani. Okay.
Same due to Aadhaar.
Yes. All right, we'll continue. Right. So before break, I don't think I told you about first 5 facts. 6th fact also. 7th fact is that all global variables are technically attributes of a module called main. Let's tell you something. Modules are everywhere in Python. Python is a fully modular language. Every code that you execute in Python, that code, whatever it's executing, right, belongs to some module, including a main program. I'll show you right here a little bit about namespaces. Modules also act as namespace. I guess you know that. Suppose we just say, I'll save this file as test program.py. I save this file as test program.py, and in here I'll just define a function called foo. For example, in this function I'll say print foo called under name double underscore name double underscore. Think of all these variables or attributes starting with double underscore, ending with double underscore, or special attributes or special variables. There's one special variable called name, which will result to the current executing namespace or the name of the module to which the execution belongs to. Right? And I'll call foo function here. To give you an understanding. There are 2 ways to run this. One, if I say Python 3 and say test program.py, when I say Python 3 test program.py, what is the value of name? It's a string which is double underscore main double underscore, right? So what is this? Yes, it is. The value of name is equal to main. Suppose you go to this Python 3 prompt. Inside the prompt, you can say import test program. Any file with .py extension can be treated as a module. When you load this as a module, foo function is called, right? It started executing every line as a part of module loading. Foo function got called. Calling foo function, try to print a message. See this? Called in a namespace test program. That means when you load it as a module, the module name is test program. To access any member of the module, you'll say test program.foo. All definitions becomes modules attributes now. All definitions of this particular program automatically transform to modules attributes. Getting? In fact, when I say dir of test program, you can see the result. It shows. Don't worry about all the special attributes. The special attributes will be there in all modules, but just with this, foo is one of the attributes we see here.
If we have a class inside the module, it will have a code attribute. Class may have a
Yes.
attribute, so it will be modules class attribute.
Yes. This foo itself is an object. That object has attributes. For example, I can say something like this. When I say test program foo, I'm calling that as a function. Functions are also objects. This object also has attribute. If you want to know what is the name of the function, you can say dot double underscore call name double underscore. You want to get the function's code, you can say double underscore code double underscore. You see, you got a code object. Code object. Getting? From the code object, you want to find out the bytecode values. You can say code dot c underscore code. This is a reference to an object. Test program is a variable referring to a module object. The module object had an attribute called foo, which is a reference to a function object. The function object has an attribute called code, which represents the function's bytecode, represents as an object. That bytecode object, you can get the actual code in raw format by doing c underscore code, which you can see with a binary byte string which you see here. dot operator can be applied for accessing attributes. Clear? Right? Now suppose if at all I say print double underscore name double underscore here. What is name in this case? A variable, right? In this case, it's main. I'll show you something very interesting. I'll say a is equal to 100, value is equal to 5.0, def greet print hello world. What are all of these? Global variables, am I correct? In the triple greater than prompt. It's not inside a function, it's not inside a class. So a is a variable, value is a variable, greet is a variable, referring to a function object, so I should be able to say greet open close parenthesis to call the function if you want to. Even test program is a variable, am I correct? Referring to a module object. All global variables are nothing but attributes of main module. Well, there is no reference to main module. You're already in main, so don't have a reference to main. But if you want, you can get that. Just try to say import main once. Import main will do two things. It'll load a module which is not already loaded. If it's already loaded, it'll return a reference to the module with that name. Now just see this. Main is a module referring to the main is a module referring to the current executing namespace. Sorry, you can see this right? Module referring to the current executing namespace. Main dot a, main dot value, main dot greet. Can you see this? Suppose we just specify test is equal to. Somebody assigned this? Somebody is not signed? Please sign. Test is equal to 5.0. You think you're creating a variable. Every variable you create apparently is nothing but adding an attribute to main module. All global variables are attributes of main module. Right? So just see this. If I just say main dot test. Suppose the main dot test is equal to hello world. This is hello world. Suppose a main dot test is equal to main dot new data is equal to test string. You know what I did? I created a new attribute for main module. Creating an attribute to main module will end up creating a new data. So when you think you're accessing global variable, when Python is getting compiled, it will translate to module dot that attribute. Think of global variables as just shortcuts to main module's attribute. Simply. What do you think as variable is just our own syntax sugar? Reality, everything is an attribute. Now in a while you'll understand there are no attributes also.
So variable is just a concept or something.
It's a concept. To make it easier for us to understand things. Like we say create a variable just cannot hang in here. It has to be attribute of some object. All variables are attributes of a module object. So local variable, it's a part of the function frame object, okay? So global variable, it's a module's attribute, right? Main module's attribute. Likewise, I should also tell you, see, all global variables are technically attributes of main module. All other modules loaded using import statement will have their global definition visible as module attributes. See, if I'm in the main program, all the global variables are main module's attribute. If I have some other program which are loaded as a module, what happens? All the global definitions of that program become that module's attributes. Remember test program dot foo. Foo is technically a global variable, right? In that program, that becomes that module's attributes, right? So modules act more like namespace this way. Clear? Next, I shall tell you, every special character used within right-hand side expression are shortcuts to special methods implemented in one of the objects that form the operand of the operator. A very large description. I'll tell you in simplicity what it means is this. The Python prompt, when I say, I'll show it in the editor. Never mind. If I say A is equal to 10, B is equal to 20, C is equal to A plus B, this is the right hand side expression, am I correct? In a right hand side expression, every special character, plus a special character, will resolve to a special method. But when I say C is equal to A plus B, this is compiled by Python as, I'll comment this line, okay? It will be compiled as C is equal to A dot double underscore add double underscore of B. say print C. Just see this. See the result? You got 30. Where it says C is equal to A plus B, this gets translated to C is equal to A dot add of B. Further it will get translated to, it should tell you further it will get translated to int dot double underscore add double underscore of A comma B. Understand it? It's a two-level translation. Every instance method will become class method with instance passes first argument. Okay, we'll discuss that in a while. This also is the same thing. Suppose we say C is equal to A into B. This is no different than telling C is equal to A dot double underscore MUL double underscore of B. You can see this? In effect, Python has full support for operator overloading. Every single special character that you see in the right hand side expression is an operator, and they map to some predefined overloaded methods. It. But what you should understand in Python is it does not let you invent a new operator. In C++, you can invent new operators. You suppose operator overloading, but you can invent. You can have an operator like tilde greater than, spaceship operator, very popular in C++, right? Less than equal to greater than. It looks like a spaceship. So you can invent new operators. Python does not let you invent new operators. Existing operators which are there, you can overload them to have some special functionality. Right? Clear with this. This follows this concept of duck typing, which I'll explain in great depth later in a while. Okay? So to all the arithmetic operators, plus, minus, multiply, divide, right? Every single arithmetic operator maps to some appropriate overloaded methods. In fact, those naming, if you want to find out what they are, I have some notes right here to demonstrate that. This is what it gets translated. When it says C is equal to A plus B, this is equal to telling C is equal to A dot add of B. Minus becomes sub method. Multiply mul. In Python 3, divide becomes truediv. Percentage becomes divmod. And you can see double forward slash truediv, power of operator, negate, it's all of this. Clear? Saying it. So it's not just with arithmetic operators. Even non-arithmetic operators, I will show you an example right here. Oh, sorry. I should have this non-arithmetic operators. For example, if I say A is equal to 10, 20, 30, 40. V is equal to A of 0. Do you see a special character here? It is an operator. This is called item accessor or get item operator. I'll show you what that means. Telling V is equal to A of 0 is equal to telling V is equal to A dot double underscore get item double underscore of 0. So you'll get the same result. See this. If I say get item of 1, it's like telling A of 1. Am I correct? A of 1 is 20. Whenever you see a square bracket operator being used in the right hand side expression close to a variable or attribute, this particular attribute or a variable has support for a special method called get item. And there will be passes name, passes a value, argument. This works even for dictionary. Even a dictionary also, when I say V is equal to person of name, when I say name in square brackets, right? It becomes person dot get item of name. It's called get item operator. But one more very important aspect I shall tell you. Remember I told you about set item? I'll tell you what this means. If I say A of 0 is equal to 100, and you do this in Python. When Python encounters a statement like this, when left hand side it sees a special character, okay, open close square brackets, Python translates this to A dot double underscore set item double underscore of 0, 100. This assignment, right, gets compiled to this particular statement below. As a proof, just see this, print of A after this, okay. See the result, 100, 20, 30, 40, right? 10 became 100. Any questions? Doubts so far with this? So I told you that Python has full support for implements every operator by implementing overloaded special methods. In summary, Python has support for operator overloading. However, it does not allow inventing or creating new operators.
So we can already set item.
If you create your own class, I'll show you an example. If I create my own class, right away, right here. Class, I'll just specify stuff. Silly example, okay? And let's assume I'll say def double underscore get item double underscore of self. Don't worry about the self. I'll explain that in a while, okay? Still, I have to explain that. I'll return John. Def double underscore set item double underscore of self. Okay, I value. Okay, I'll just say print setting I to value. Just see what happens. S is equal to stuff. Okay, print of S. Stuff is my own class which has two special methods implemented called get item, set item with this prototype. When I print S, right, it will tell you it's a staff object. Just see this now. When I run this, it will tell you that it just created a main.staff object. After this, when I say over here print S of 100, it doesn't matter. He's not really worried about what the value of I is. It's a print S of 100. S of anything will return a value called John. See this? So you could have your own logic here where, where's my mouse? Oh, my mouse vanished. Oh, the mouse got stuck. I think my mouse battery died. Okay, never mind. Alright, so you can see here, we say main.staff object at so and so, right? So John, which means that if you say S of and you give anything like this, it will become S dot get item of 100. I am not trying to make any sense out of that argument being passed. In reality, if I create my own custom container or collection, I could actually go to that slot, 100 slot, get a value. And how to maintain a slot, right? If I say set item of, when I set something like this, just see what it does. If I just say S of 50 is equal to Smith. Just see what happens. I'm just trying to do an assignment, right? S of 50 is equal to Smith. The S is like my own object. I'm using some index operation, right? To set a value. See what happens when I'm running this? Setting 50 to Smith. Whatever statement got executed, just see, when I said S of 50 is equal to Smith, it became S dot set item of 50 Smith. 50 becomes this argument, Smith becomes this argument. Clear with this? Right? The square bracket is nothing but an operator. If you implement these two operators, these two methods in your class, it works with square bracket operator, both for get and set kind of operation. Any questions, doubts so far? Right? In fact, this gives you some interesting hints. For example, I'll say A is equal to 10, 20, 30. It's a list. I'll say B is equal to 10, 20, 30. What is this? A tuple. What is the difference between a list and tuple? Quickly.
Tuple is mutable. List is mutable.
Tuple is immutable. What do you mean by immutable? You can say A of 0 is equal to 100. You cannot say B of 0 is equal to 100. Am I correct? I'll tell you why. I said, I said B of 0 is equal to 100. Failed. Correct, right? So, why? Dir of A shows, when it's a dir of A, you can see the set item method. There is also get item method. That means you can access item, you can set an item. When I say dir of B, you can indeed see get item, but you'll never see set item. Because that method is not there, it throws this exception. Clear with this? Any questions, doubts so far? That's how they made it immutable. That is, you cannot change anything. There is no way to modify any elements. They didn't provide any methods to modify them. Clear? So, I told you that every single operator can be overloaded in Python, all special characters. And fact number 9, functions and classes are first class objects like numbers, strings, lists, and so on, just that they are callable objects. Let me tell you something very common between a class and a function. Just see this. I keep this mouse aside. I can't use this anyways. Suppose if I say def foo print foo function called class car def init car object created. When I say foo open close parenthesis, what exactly happens? It executes the body of the function. This call operator is to execute a body of a function. When I say car open close parenthesis, this is called as a constructor expression. Technically, you're calling the class will construct an object of the class. It's a constructor expression. So you can see it says car object created, return value will be a main.car. You can see a car object return over here. So in effect, both the function and the class understands open close parenthesis. Any object that understands open close parenthesis operator is called as a callable object. To check whether an object is callable, you can use a introspection function, callable of foo, callable of car. You see this? Callable is a built-in function to check whether it understands whether the object, right, target object understands call operator. Actually, when you say foo open close parenthesis, foo open close parenthesis like this, right? There's nothing but a shorthand to say foo dot double underscore call double underscore and like this. When you call an object, it invokes the call method on the object. When I say car open close parenthesis, there's nothing but a shorthand for telling car dot double underscore call double underscore. Actually, some of you might wonder, what about this? This method also is a callable object. Am I correct? So you should be able to say dot double underscore call double underscore like this also. That call also is a callable object. You say dot double underscore call double underscore. Can go up to infinity. And actually, this is implemented in C, so it will work. Methods are also callable objects. Just when you try to call a method, right? That last open close parenthesis is implemented in C. C Python. Okay, so you can see call. So you can think of this call, right? Indicates that an object is a callable object. So dir of any object. If you see double underscore call double underscore, you can call it. Just see this. Dir of foo. Foo is an object, am I correct? Foo is referring to a function object. Function object also has attributes. What are the attributes of function object? See this? Call. Likewise, when I say dir of car, unfortunately for car, it doesn't show anything here. Call is not shown. Why? Because it is inheriting from its ancestor. It's going through some inheritance hierarchy. So if you look at car, right? Car has a base class, which is object. So you say dir of object, right? Even object doesn't have call, sorry. It also has infusing of type. It's an instance of type. If you say car is an instance of type. Now we say dir of type. All types are callable objects. Types are callable objects. Clear? It's coming by inheritance hierarchy. Inheritance or instance hierarchy. Okay? So coming back to this. Functions or classes or first class objects like numbers, strings, lists, and so on, just that they are callable objects. Calling a function executes its body in a new frame. Right? Whenever you call a function, a frame object is created. Dynamically, a frame object is created. We call them a stack frame in other languages. We call them frame object in Python, and the function's body is executed in that frame. The frame object will represent all the local variables and local definitions in that function. Saying it, masking of the global definitions. Calling a class instantiates or creates a new object inheriting all the attributes of that particular class. Okay, that's what it does. Attributes of an object in most cases are technically keys of an object's internal dictionary. Some time back, I made a shocking revelation telling that there is no global variable. All global variables are nothing but syntax sugar for modules attributes. Am I correct? All attributes of an object, almost all attributes of an object, are nothing but resolved as keys of a module's attribute dictionary. So when you create an attribute, like when I say over here, do I have that particular Python prompt still there? I think I came out of it. Let me go back to this Python prompt. Remember, it's A is equal to 100, name is equal to John, right? When I say this, when I say import main, telling A is same as main dot A, am I correct? Or name is similar to main dot name. When you see a dot over here, in this case, what happens? Every attribute or every object has a built-in attribute dictionary. So there's a dictionary over here. So when you actually say main dot A, this again gets resolved as mains dictionary of A. Main dot name gets resolved as main dot dict of every attribute that we create. Every attribute that we create technically become keys. The name of the attribute becomes the keys of a dictionary. The value will be the reference to the object they refer to. Suppose in my Python prompt, when I say something like this, when I create a class, I'll show you an example here. Maybe class car. Okay, def double underscore init double underscore of self. As a self dot name is equal to Toyota. Self dot owner is equal to Smith, and self dot color is equal to red, and C is equal to car. I'll try to run this. Execute this. The Python shell. You have a variable called C. C is reference to a car object. C dot name will tell you what's his name, Toyota. C dot owner tells you it is Smith. C dot color tells you it is red. Actually, when it's a C dot name, this in this case get resolved as C dot double underscore dict double underscore of name. So every object's attribute is maintained in a dictionary. Every object will have an attribute dictionary associated with it. So all the attribute resolution, right, happens through the dictionary. Clear with this? Right? There's something you should know. All these are internals that you should know about Python. Last fact I should tell you is about if attributes of an object refer to data, they are treated as object's properties. If attributes of an object refer to a callable object, functions for example, then they are treated as objects' methods. The difference between a method and a property in Python is only simple. Methods are callable attributes. Properties are non-callable attributes. That's all. We use a generic term called attributes to represent both methods as well as data attributes, okay, in Python. In summary, Python does not differentiate between data or method and object. They are inherited, resolved in the same manner. Okay, you should know. And last, every object in Python can fully be introspected in runtime. This allows duck typing as a means of object-oriented programming instead of generalization, inheritance-based design. In Python, it's very uncommon to use class hierarchies. You work in Java, C++, right from the learning days. Let's start with abstract classes. Abstract class shape. They'll have a shape called circle, then you'll have, let's say, a square and so on, and you'll have a virtual function in shape called, let's say, area, find area, and we'll implement them in the concrete implementations. Am I correct? So we call abstract methods and abstract classes. We very rarely see complex inheritance hierarchies in Python. Because Python uses a complete opposite approach of inheritance hierarchy, which is called as duck typing. Duck typing is actually a terminology which is taken from a very familiar quote by a poet who lived sometime in the early 19th century. His name is James Whitcomb Riley. He says, when I see a bird that walks like a duck, swims like a duck, and quacks like a duck, I call that bird a duck. What do I mean by that? See, when you have to learn how we humans interact with objects, we don't really care about class hierarchy. Let me tell you something. Imagine you're a small kid, or you have a small kid, 3-year-old, who's learned how to speak. And that kid shows one bird and asks, what's that bird? You don't take up your biology class or zoology class and say this is a bird falling to the avian family, belonging to so-and-so genus, so-and-so. You don't do that. You look at that bird and say it's a crow. That's it. You'll just name that bird as a crow. Now, that kid's common sense will automatically identify that object based on the attributes. Am I correct? What are the attributes? The crow is black in color. It's got a particular shape. It's got some particular shape of wings. It costs. He looks at the attributes and he identifies a bird. Next time when he sees a bird that's black in color, he'll think it's a crow because the color is black. It also looks like crow. but it doesn't caw, maybe it coos. They say, okay, it's not a crow. Because crow caws, but this is doing a cuckoo, so it's a cuckoo. So you identify objects based on their traits, their attributes. Damn unit is an attribute. Remember some time back I created a class called staff. The class called staff, I put get item, set item. Python will think it's a container, it's a collection. Because I can actually store values based on the slot or get values based on slot. If at all I create a class, implement a method called add, subtract, multiply, divide, float div, all the arithmetic operators, Python will think it's a number. For creating a number, you don't have to inherit any base class. Just create a class implementing all the arithmetic operators, enough. If you want to create a collection, create a class with appropriate collection properties. Its iterability, all collections should have length. And some collections could be indexable. You provide this particular protocol, every part of Python will assume it's a collection. Right? It's duck type based object orientation. Clear? In fact, duck typing introduces a lot of interesting features. For example, A is equal to 10, I'll say 10, 20, 30, 40. B is equal to 40, 50, 60, 70. C is equal to hello world. D is equal to, I'll just specify name, Sam, place, Bengaluru. A is a list, B is a tuple, C is a string, D is what? A dictionary. We have different data types here. I can say len of A, len of B, len of C, len of D. You have a built-in function called len that can work on all these kinds of data types. Do you think len function knows how to iterate over a list to find out the elements, or how to iterate over a tuple to find out its elements, or how to iterate over a string and find out its elements? No. It is a generic function. Most generic functions, I will say 90% of built-in functions are generic functions. You know what are generic functions? When you say len of A, len does not know about what A is. It does not even know what type it is. Blindly len of A will call A dot double underscore len double underscore. Every generic function will invoke a responder method on an object. Another way of understanding duck typing is, an example I tell you is, imagine a small kid given with a stick. A naughty kid, of course. A naughty kid with a stick, you know what he'll do? He'll try beating everything. He'll beat the desk, he'll see what sound it gives. He'll beat the glass, he'll see what sound it gives. If you're not attentive, he'll beat you and see what sound you give. Different objects respond differently for the same action. Same action, different objects respond differently. Some objects like you will raise an exception. Right? Don't beat me, I will beat you back. Right? You'll raise an exception. Some objects will respond back positively with the sound. Right? So that's what you can see here. When I say len of B, is telling B dot len like this. This is called duck type based object orientation. A very practical object oriented design in comparison to the purest core design as prevalent in C++, Java, C#, and the statically typed languages. In statically typed languages, you will actually explicitly say array.length. Because all of us made to believe that you can't have a function outside an object. Every function must be a method of an object. Right? That's what we made to believe, at least from Java perspective. Like for example, I can have this marker and I can have this glass. Is there any relation between this marker and this glass? No, I can't draw a relation between these two. This marker is a writable object, it's a drinkable device. You can't write with this. You cannot drink with this. You should not drink with this. I mean. Right? So there's two dissimilar, unrelated objects. If this comes from a different class hierarchy if needed, this comes from a different class hierarchy. I can say marker.write, glass.drink. Right? I can weigh this marker, weigh this glass. What is weigh? Generic function. Each object responds differently to this. Right? I can weigh this weight, throw this marker, throw this glass. You can see generic functions being used here. The objects might respond differently. Some will raise an exception. They don't have a responder method. They have a responder method. They will respond positively. Right? That's how it works. For example, if I just say over here, E is equal to 100. What is E? It's an integer, right? It's a number. What happens when I say len of E? Do numbers have length? No. Only collections have length. collections of items alone have length. Only collections have length, not numbers. Object of type it has no length, it's an exception. Why? Because it tried to look for len attribute in here. There's no len attribute in A. So when it says E dot double underscore len double underscore, this raised an exception perhaps. This exception is translated to int object does not have length. Trying it. Clear with this? Understood? This is one of the interesting approaches of object orientation, makes your O design much simpler and more practical. May not be purist, but more practical, right? In Python.
One question.
Yeah.
So when we then assign something, say A equal to some string or A equal to some number,
Yeah.
that object is init in one case and string in other case.
Yeah. In one case, yeah.
So it's basically calling a factory pattern to create that object to determine it is an integer or a string.
Yeah. Basically, literal, right? When you see the literal, like say A is equal to 10, the literal representation will actually call int of 10. It calls an int constructor. When you say hello world, right? Double quotes hello world. When it sees a quotes, double single quotes, triple quotes, that means it knows it has to create a string object with the value hello world. There's Python internal syntax wiring that takes care of it for literal to actual object conversion. Other case we explicitly convert. For example, we don't normally do this, right? We say A is equal to 100. There is a string. You can't do any arithmetic on this. Python is dynamic but strongly typed. What I mean by strongly typed? A string is a string, not a number. You can never do A minus 45, will not work. You see that? Even A minus 45 will not work like this. Because strings don't understand subtract method. You want to subtract, the string must be converted to integer. How do you create an integer? Int of A. It's a type constructor. It's a constructor expression. Int is a class. Construct an integer object using a compatible object. A compatible object could be a string with numbers. Clear with this? In this case, you're using explicit construction. In many other cases, when you use literal, automatically it's constructed. It's similar to autoboxing in Python, in Java. Autoboxing we say in Java, right? Similar to that. Yeah? Any questions, doubts so far? Next I shall tell you, fact number 13. Python allows monkey patching, module objects, custom function objects, custom class objects, and instance of custom class objects. What is monkey patching? Monkey patching is nothing but I am given an object. I can remove some attributes which I don't like. I can add my own new attributes. I can change attributes. This kind of modification of attributes for an object is possible for what? Modules, any function that we create, any class that we create, and instances of that class that we create. So class objects, instance objects, module objects, and custom function objects can be monkey patched. Monkey patching is a useful feature. Some people think, oh my god, why would I want to change the attribute of an object? It gives a lot of interesting possibilities. In fact, used by some of these fantastic libraries like gevent. Gevent library relies on monkey patching. Maybe a socket implementation will always block if there's no incoming data, let's assume. When I use gevent library, it will patch the socket attributes in such a way that instead of blocking, right, relieve the CPU to the underlying lib event layer. So if any other socket has any incoming data, we can go to it. So you can do IO multiplexing. Without having to change your code will work seamlessly. Right? That's one of the interesting features. I'll show you more about it later on. This allows complete runtime customization of objects on demand. One example of monkey patching I will show you right here.
One question is,
Yeah.
so some program is running, if we get some output from an object,
Yeah.
we can add our attribute to it. So how is security?
Security from what?
Some program.
From
we
whom?
can add-
Security from whom? Programmer?
Someone can hack it, right? If we can add
Who?
attribute.
User or a programmer? Are you telling me that Python objects are given to user, so user can type Python code? No, it's for a programmer. Programmer. You know, security is the most abused terminology in object orientation. They say encapsulation. What is encapsulation? Security. Security from whom? Another programmer who has access to your library? Come on. If I have access to your library, I'll modify your library code. Getting? Don't think of security. That word security is an abused term here. Some books will tell you, encapsulation gives security. Security is like, abused term. Don't think of security as, user security. Users have no access to your program. Users only interact with your program's running program. They don't have access to your Python interpreter there. Am I correct? Am I correct? If you're able to allow a user to execute and implant a Python program, your design is botched. Any language, whether it's Python, C, C++. You provide an interface where you take input from a user, which is data, validate data, do something. But when I am a programmer who is taking some library developed by another programmer, I am given complete freedom to choose what I want to. That's the interesting part. C++, Java, you give a rigid object. You know what's the problem? Rigidity there? If I want to debug, identify some bugs in the class that I did that from somebody, it will become almost impossible. With Python, because it's an open box for a programmer, you get a lot of wonderful things. Okay, there's a concept I covered in Python Beyond Basics, but also in Core Python, but most of you will skip that and attend it here. Remember, there are just two kinds of programmers, or you can also say there are only two kinds of people on this earth. Let's stick down to programmers. Stick to programmers. Programmers who are self-disciplined. All dynamic languages expect programmers to be self-disciplined, including Python. And the other, programmers who need to be disciplined. Python is not for you. If you're a programmer who thinks, oh my god, I might make a mistake, my team might make a mistake, Python is not for you, not for your team. If you're working on Python, you know what you're doing. Python will not come in your way. There's a thing called security there. Python will not secure itself, say, oh, I've given an object, you should not touch this attribute. If you touch this attribute, hell will break loose. Don't touch this attribute, do it. No problem. You know how Python's encapsulation works as? Like real world. You bought a TV. And the TV went bad. One option is you take it to the service center. Option 2, you'll tear off that label, warranty void or seal broken. Just don't care about it. Use a screwdriver, open it, fix it your own self. Python, the other way. Python's mindset is the other way. Problems are fixed by fixable. Right? You don't have to depend on somebody who's vendor of a library for all your support. Clear? That's what this is. It's a design choice. I'm not trying to say this is good or this is bad. It's a design choice of Python. All dynamic languages assume this. Clear? Now coming back, I told you, the complete dynamic design of Python expects programmer to be self-disciplined and responsible when it comes to program design and development. I told you that, right? The language does not stop the programmer from mistakes, like misspelling variables during definition, changing objects attributes without proper design thinking. If you're removing an attribute, you better have a proper design thinking for that. Why removing an attribute? There should be a real reason to do so. Without reason, if you're removing an attribute, your logic is wrong. Nothing to do with security there. Rethink on your logic. Clear? So this is. In fact, the funny jokes I can tell you is about selling points of these three languages. This Bajaj Frost to sell C++, in one of his book, C++ programming language, right? He's made a quote. He said, C makes it easy to shoot yourself in the foot. C++ makes it harder. But when you do, it blows your whole leg, blows away your whole leg. You know, C++ is designed like a rifle. C is like a pistol. C++ is like a rifle. You cannot point a rifle at your own self and shoot. But with great difficulty, you can point upside down and pull the trigger. And you know what happens? It will not punch a hole, it will just blow your whole leg off. That's the power of a rifle. James Gosling, in his way of marketing Java, said, Java is like C++ without guns, knives, and clubs. You know what that means? People abuse multiple items. Remove it. People abuse operator overloading. Remove it. People abuse, friend functions and friend classes. Remove it. So they removed all the features that makes programmers hurt themselves accidentally, right? And Java is more restrictive language because of that. Python is all about this. When people ask Gadav and Rasam, about Python, one thing about Python you have to observe is indentation rule, right? Very strict about indentation. He says Python is an experiment on how much freedom programmers need. Too much freedom and nobody can read another's code. Too little freedom and expressiveness is in danger. Python strikes a balance. It forces you to write readable code. Code must be readable. That's why indentation rules come into play. There's some strict PEP documents now available, style guides and so on. The other two, they say talk about Pythonic way of problem solving, right? But at the same time, it gives you complete flexibility on your freedom of logic. How you want to logically express your code, it's up to you. Python doesn't come in you. So it strikes a balance in both points. Okay? So you should know that. Before lunch, I'll show you this, of course. Okay, post lunch, if you see this, you'll get frightened. Before lunch, I'll show you. This one single diagram is a complete OOP architecture of Python. To understand this, you understand O in Python. This is one diagram. I'll tell you what this is all about. There are two top level objects in Python. One of them is called as a type that decides a type of every other object. Every object should belong to some type, correct? Every object should belong to a type. If I show you an object and what type it is, since it's a marker, it's a glass, it's a bottle. For typifying objects, there's a root class called type. And the root class itself is an object. You can't have non-objects in Python. Every class is an object. Even type class is also an object. There's also an object called object. I can tell you one thing. For example, if I ask you, if I show you this particular object, I ask what type it is, it's a marker. It's an instance of marker. That's how you say it is. This object is an instance of marker. But this marker is made up of the same ingredients, similarly, to this bottle, plastic, or to this ingredients also, atoms. You know what I mean? What I'm trying to say over here? Every object, concrete object, will have some common attributes and common properties. Like we say, everything is matter around us, right? Everything is made up of matter, we say. Similarly, this object will have common information about all objects derived downstream. What is it? Every object will have an object's ID. Every object will have some attributes. Every object is introspectable to check what attributes they have, what are the attribute dictionaries, and so on, right? That information is deriving from there. Think of this object is a root of the inheritance hierarchy. You know what I'm trying to say? Inheritance hierarchy. If you ask one class, what do you inherit from? What do you inherit from? What did you inherit from, right? The root of the hierarchy will be object. In fact, these dots are these. Inheritance relation is green colored arrow mark. Instance relation is this particular purple or whatever color it is, arrow mark. You can see it. These two are intertwined. If you ask an object, root object, what are you? He'll say, I'm an instance of type. Instance of type. See, instance of type. If you ask type, what are you? He'll say, I'm an instance of type itself, but I'm a subclass of object. Subclass of object. Assigning it. So in the class hierarchy, right? The class hierarchy, this stands at the topmost. In the instantiation hierarchy, this stands in the top. What is instantiation hierarchy? It's very confusing. You want interesting part. In studying great languages, you only say classes, objects. That's it. In Python, we say meta class, sub-meta class, class, object. You know what I'm trying to say over here? A meta class can be used to create class instances. Classes are instances of a meta class. A meta class itself can be an instance of another meta class. That's called instantiation hierarchy. But instances can go through a hierarchy. In a simple example, you can say only two levels. You can say there's a meta class. All of these are instances of the meta class. All of these are instances of the meta class. I'll show you an example here. When I say A is equal to 10. A is a variable referring to an object 10. So it's a type of A. Type is a built-in function to identify a type of an object, which class it belongs to. It says int. I will say B is equal to type of A. Type also is an object. I'm getting reference to the object's type. B is referring to the type of 10. So look at B, shows int. If you ask what is a type of B, it says of type. Type is a meta class for int, float, string. Your class, for example, I'll create my class. I say class car, pass, empty class. I'll create a subclass also. Okay, as a class SUV of car. This is how we create subclass. What I'm trying to say is that this SUV is inheriting car class, right? Inheriting car class. I'll say S is equal to SUV. S is equal to SUV. Type of S will tell you it's main.SUV. This I'll say type of S, right? I'll just say it as A is equal to type of S. A is nothing but referring to the type. The same as SUV. See this SUV will print main.SUV. Am I correct? Type of A will tell you its type. When you create your own class, every class that you define, you're creating an instance of a type. So every class is nothing but instance of type. All of these are instances. This is the arrow mark, right? The instance of relation. Int, string, list. If I create a class called staff, staff is also instance of type. Clear this? If I create manager, manager also is an instance of type. In this example, I'll use a similar example. I'll just create something called staff. Forget about car. As a class.
But these are not concrete objects, right?
Yeah.
The classes that are created from type.
How do you know it's not a concrete object? Everything is an object. There's nothing called concrete or abstract here. Everything is a concrete object here. Classes themselves are tangible objects. Tangible. You know what I mean? You can do things in a class like you do with a normal object. Nothing called abstract objects in Python. Every object is tangible, including meta types also. That makes object orientation fully uniform. Every object is seen identical in that sense. Okay?
So SUV is like a subclass of car, right? So how do you get like
I'll come to that. I'll come back to the other example. I say class staff pass, class manager of staff pass. What do I mean by telling that? Manager subclass of staff. The instantiation hierarchy is this. If I say S is equal to staff, M is equal to manager. If I say type of M, manager, type of S, staff. If I say type of S, what do I mean by that? Get the type of its type, right? Type. What is type of M? Type. This is how instantiation hierarchy works. By default, there are only two levels. See? Manager, this M, right? M could be an object, which is an instance of manager. Manager is instance of type. S could be instance of staff. This member could be an instance of staff. And staff is an instance of type. But however, there's something called inheritance hierarchy. To know inheritance hierarchy, you could say inheritance can only be for class to class, never to objects. Objects, right? By default, always inherit their classes. Which means I can't say m dot base. This is a special attribute to find out the superclass of this particular class. Only classes are superclasses. See? It says manager object has no attribute base. I'll show you something. Manager is there, right? Manager is a class. Manager dot base will tell you it's staff. Staff dot base will tell you object. If you look at object dot base, nobody. Object is root of inheritance hierarchy. Inheritance hierarchy, object is root. I'm trying to say that there's something called matter. Matter is made up of solid, liquid, gases. Among solid, you have, let's say, plastic. Under plastic, you have maybe a white colored plastic, polypropylene, polystyrene, different plastics. And this pen is an instance of one of these plastics. That's inheritance hierarchy. Inheritance hierarchy. But this, what do you say this is? This is a marker, and marker is a pen. You can see that, right? Instantiation hierarchy. You have instantiation hierarchy, inheritance hierarchy. There are two parts which you can look up in Python. See, let me tell you, this is not just in Python. Any pure O languages support this kind of object orientation. Because any pure O languages will treat classes themselves as objects will have a notion called meta classes. Right? Which means you can get a meta class of your own also. That's also possible, right? And you get a class hierarchy this way. So this is how you can relate to objects in Python. All of these are actual concrete objects you talk about, like in other languages. A is equal to, if a score is equal to 10, there's a variable having a value 10. 10 is nothing but an integer object. How do you say integer? It's an instance of integer class. Which class? This class is an instance of this type class. When I say user is equal to guide in double quotes, there's a string which is instance of class str. Str is an instance of type. All of these classes by default will inherit object. Through object you get to know ID. Every object will have a unique ID. Every object will have memory footprint. Every object will have attribute accessibility. All the things are coming from here. The types will signify special features that you can do on a class. Like integers, you can add, subtract, multiply, divide. Right? Special methods are implemented in this. Look at this particular example of manager. See this? From the instance hierarchy, it is directly a type. It's an instance of type. And this is an instance of manager. Inheritance hierarchy is an instance of manager, of course. This manager is inheriting staff. Staff is inheriting object. So you can say that any object, right, will get attributes via inheritance hierarchy and instance hierarchy. Always. The instance hierarchy will tell you about the make and the features, specialized features. The inheritance hierarchy will tell you about generalization features. Okay? Clear with this? Any questions, doubts so far with this? So in summary, I told you, classes represent specification of concrete objects. Classes in real world are just an abstract representation of a collection objects that have similar properties and behavior. In real world, you don't really see classes, do we? No. When I say pen, you don't see a pen. You see an instance of a pen. Pen is just an abstraction to represent object that has some common traits and properties. Right? Class are merely an abstraction. But in Python, classes themselves are objects. So actually, when you create a class, this is what happens. We can dynamically create a class. I'll show you how. When I say class, and let's say staff, okay, and inside staff, let's assume I'll forget staff files. Okay, let's be there, no problem. I say class manager of staff. I say like this. I'm trying to say this manager is inheriting staff, and then maybe I have some class attributes inside. Class attribute could be, I can just specify company is equal to Cisco. I told you all definitions inside a class become class attributes. Am I correct? When you create something like this is what happens. This can also be created another way. I'll call it as manager2. I'll say manager2 is equal to type of. First argument would be the name. That is, the name must be called manager. Second argument would be a tuple indicating what are the class. What are the base classes. I'll say it inherit staff. The last attribute would be a dictionary of the attributes. Oh, actually, hang on. Oh, there are two meta classes. Okay, I'll do one thing. Meta class must be non-strict sub. Yeah. Yeah. Yeah, it should be there. Okay, let me just say MGMT or something. No, I think I made a mistake. It should be first the dictionary, then the base class, I guess. Oh, I made a mistake. Okay, it's correct. Okay, staff I put in quotes, right? It's not in quotes. I put this in quotes, should not be in quotes. That's a mistake. So just see this. When I say class manager, sometime back I said this like this, right? Class manager staff, company Cisco is similar telling manager is equal to type of name of the class, what class it derives from, right? And what are the class attributes. It defines a class. So it defines a new class now. Not an object, it's a class. In fact, we can say over here, see this manager 2, right? In this case, when I say this, right? So not here, it's this one. Right? See, the manager 2 is actually a class object. See, main.manager. See, M is equal to manager 2 will instantiate a manager object. You can fully create a class and has a right answer expression using, if you know this syntax, right? This branches into another part called metaprogramming in Python. But metaprogramming, I'll tell you what Alex Martelli says. Alex Martelli is one of the gurus in Python. He can implement a lot of features of Python object-oriented features, right? In Python 2.0, his contributions are immense. When people ask him about meta class and metaprogramming, he says 99% of the time you don't need to know it. Even if you know it, you'll never find a use for it. It's just good to know, but you'll never use it. Okay, that's what it is. It's just to know the internals. Clear? So I just told you that they are created using the class definition or by using type. Class are callable objects. Calling a class creates an instance object. All instances of a class share the attributes of class via class instance inheritance. Now I'll tell you the ABC's object orientation. Before we break lunch, what I'll tell you is, let's come back to the ground basics. Okay, I'll just say, I'll use cells over here, makes sense. I'll say class car, silly example. I'll say pass. I create an empty class. This, when I say pass, I mean the class body is empty. I create a class which has no ingredients inside it, empty body. Okay. C1 is equal to car. C2 is equal to car. I'll say print C1, C2. Let's execute this. See the output. Oh, then execute or not. Execute the cell now. Just see this. See output. Main.car object with some number. This is object's ID in hexadecimal. There is object ID in hexadecimal. There are two different car objects being created. Right? Now, does this car object have any attributes? Is there any attributes in this car object? Let's just check. I'll say print dir of C1. Dir will return the list of attributes of an object. Am I correct? I'll run this. Show you the output. It looks like it inherited some of these attributes from the class. Don't worry about this. All are special attributes. Is there any non-special attribute here? None. So means any attribute without that double underscores surrounding it. Alright? None of them. I'll show you something interesting. And now I'll say car dot color is equal to white. Right? Print C1 dot color. Print C2 dot color. I'm trying to access an attribute called color via C1 and C2. Am I correct? But I set the attribute for the class. See the result now? White. First rule you should know is all instances inherit class attributes via instantiation relationship. Not via inheritance relationship, but instantiation. Instances will have access to this. When you actually say C1.color, you know how it got resolved? I'll tell you how it got resolved. Every object has its own attribute dictionary, am I correct? I'll print both of them. Just see this. I'll say print C1 dot double underscore dict double underscore. And say C2 dot double underscore dict double underscore. See the attribute dictionary of this both of the objects. They're empty. These objects don't have anything in their attribute dictionary. Look up the class attribute dictionary. Print car dot double underscore dict double underscore. Right? In this attribute dictionary, you can see there are a couple of attributes that's there, but one of the attribute is color white. Do you see this? Color white. I said car dot color is equal to white. It became car dot dict of color is equal to white. Remember that? All attributes is nothing but items of the object's attribute dictionary. Now, when you actually said print C1 dot color, you might be assuming that it will be C1 dot dict of color. It will not work that way. It will throw a key error. You know how it got resolved as? When you try to run this, right? How did it resolve to white? This is how attribute resolution worked this time. It worked like this. It checks. This becomes print C1 dot double underscore dict double underscore dot get of color. Get method is a very safe method. If it's a dictionary.get, it will return the value if the key is found. If the key is not found, it will resolve to the second argument being passed, C1 dot double underscore class double underscore dot double underscore dict double underscore dot get of color. I'll run this and show you. See, you got white here? Actually, when I simply said C1.color, right, what it did was, dynamically independent check. This dot operator, what it does, it checks whether color belongs to this attribute dictionary of this object. This is not an object's attribute dictionary, this is not a class, this is a concrete object, right? It will check which class it belongs to. Which class it belongs to. It will go and check in that class attribute dictionary whether there's color. It's found, it will start to it. This happens dynamically in runtime. Dynamically. So attributes are resolved in runtime using this technique. Understanding it? It is called attribute resolution or MRO, we say, method resolution order. In what order? First it will check whether the instance has an attribute. If the instance does not have an attribute, it will go and check whether its class has an attribute. If the class does not have it, it will go and check its superclass, base class. Suppose if I created I'll just say class SUV, right, of car, pass. Now we say S is equal to SUV. Print s.color. What will be the output? I'll put in a separate cell. What will be the output? Let's see. White.
But you told it takes from the instantiation hierarchy, right? But then in this case it will be inherited.
Both. Attributes are resolved via instantiation hierarchy from objects. From the classes, it will go via inheritance hierarchy. It goes by inheritance hierarchy. It gets by the instantiation hierarchy. If it's not found via that, it will look up the inheritance hierarchy. Always. In this case, just see, when I say s.color in object got resolved, it got resolved like this. It's like telling print s dot double underscore get double underscore dot get of color. It will try to get it from the instance. The instance does not have it, it will check the class that this instance belongs to. S belongs to a class called SUV. Check its particular dictionary. This is the instantiation hierarchy path. Now, if the instantiation hierarchy does not find it, suppose color is not there here, this case, it will not stop here. It will go to this particular class. Dot double underscore base dot get dot double underscore dict dot get of color. These are it results. See, I just executed it. See the output. Actually, you can see the single dot operator did lot of lookups. Just happened dynamically. When I say s dot color, right? We check whether color belongs to the actual object, SUV object. SUV object does not have color. Then we'll go and check the SUV class. SUV class also does not have color. Then we'll go and check whether SUV has a base class. Right? SUV is base class. Say SUV is base class. SUVs, this s dot class is SUV. Dot base will represent car. Does car's attribute dictionary have color? Is resolved. If it does not resolve even all the way till here, you'll raise an exception, attribute error. This is how attributes are resolved. First via the instance hierarchy, then via the inheritance hierarchy. Clear with this? Any questions? Doubts so far with this? Right? In fact, if you know by now, learning Python, is learning how an engine works through a glass box. If you take Python as an engine, right, it's like a glass box. Everything is visible inside. All in runtime, you can introspect and do things. You don't have to read through books and theory. So I'll not dry. You can introspect and verify this. Clear? Any questions? Doubts for this? So this is how you can see the rule, as I told you, is instances inherit class attributes. The classes do not have those attributes. The attributes inherited by the superclasses. That's right. That's how it works. Now the next rule. Remember C1 and C2 are two cars are created, right? C1 and C2 are two cars. I'll say C1 dot color is equal to red. Car dot color is white. I say C1 dot color is equal to red. Now you know what happens? Print C1 dot color, C2 dot color, car dot color. So what will be the output? Yes. Red, white, white. Very clear. So what do you learn from this? Instances can override class attributes. When I say instance dot attribute is equal to value, you're getting an instance specific attribute and override the same name class attribute. Right? Now see this. Rule number 1, all instances inherit class attributes. Rule number 2, instances can choose to extend or override class attributes. Right now I'm overridden the class attribute. I can also extend it. I can say C1 dot owner is equal to Smith. Right? I say C1 dot owner is equal to Smith. I say print C1 dot owner. Okay, just see the output. It shows up as. No, I think I didn't run this. I guess, did I? No, wait. I said print C1 dot owner. I'll just rerun this again. Let's just select this up. Okay. See? Smith. But if I try to say print C2 dot owner, will this work? No, it will not work, right? Why? Because C1 has an owner, C2 does not have it. So you can add attributes specific to different objects. So I run this now. You could see car object has no attribute owner. Right? There's nothing but you're having an extended attribute here. C1 has an extended attribute. In fact, as a summary, I'll do one thing. I'll just comment this line off. Instead, I'll just say print C1 dot dictionary C2 dot dictionary. See the output. C1's attribute dictionary has color red, owner Smith. C2's attribute dictionary is empty. Actually, when we say object dot attribute is equal to value, you'll always add an element in the attribute dictionary. So when you say object dot attribute, you'll first resolve in this dictionary. If it's not in this dictionary, you look up its class and its superclass dictionary. Resolve from there, right? This is traditional. So we can see how instances can, override class attributes. By default, all instances share the attributes of class via class instance inheritance, but instance can either extend or override class attributes. The last thing I will show you is let us assume both these cars have name. C1 dot name is equal to Toyota. C2 dot name is equal to Honda. And I have one function. Remember, this is just a function. I create a function called drive car of C as a print driving C dot name. So I created a function which takes an argument which supposedly a car object and tries to access an attribute of the car object and prints it. So when I actually call this function by telling drive underscore car of C1, just see what's the result. Driving Toyota. Drive underscore car of C2. What is the result? Driving Honda. Now this function is aware of the object's attributes. Am I correct? Object's attributes. This function is supposed to be specialized. It knows about an attribute called name for an object. These kind of functions are best transformed as methods. What are methods? Methods are functions that have full access to objects' attributes, specialized to work on objects' attributes. For example, if we take this real world object called marker and say marker.write, the write method is specific to the marker's ingredients. So that attribute, write knows about how to extract the ink and make it work on the board. That's what is specialization, right? So you can think of methods are specialized functions that knows how to deal with object attributes. To transform a function to a method, all you need to do is car.drive. What am I doing? Class attribute. Car.drive is equal to drive car. I could actually now say car.drive of C1, car.drive of C2. See the result? It will be the same. Same, right? The shorthand syntactic notation for that is, you could say C1.drive, C2.drive. Let's see the result. Still you get driving Toyota, driving Honda. A very close observation. When you say an instance object dot something, open close parenthesis, nothing but is a method call. When you invoke a method on instance object, and if this method is inherited from the class, it will always be translated to c1.class, which is car, dot drive of c1 passes argument. Always. Python will wire the syntax like that. So when you actually say c1.drive, this becomes translated to, this get translated to this particular syntax. c1 dot class dot drive of c1, which is nothing but as equivalent to car dot drive of c1. Am I correct? This is called as an instance method. What are instance methods? Methods that expect the first argument to be an instance of an object, instance of the class. Right? So what does drive take? Drive car takes an instance, right? And it works on the attributes of that particular instance. What if I have a function like, say, a function called sell, which takes no argument, print, sold this car. And what I'm going to do is I'll say car.sell is equal to sell. Like I did, right? Car.drive is equal to drive car. I say car.sell is equal to sell here. For c1.sell, will it work? You know what error we'll get? I'll show you. Cell takes no positional arguments, but one was given. When you actually said card c1.cell, Python translated to card.cell of c1, but cell function that I create doesn't take any arguments, so it's an error. So by rule, you should know that any function that should be mapped as an instance method should at least have one argument, the first argument, which is reference to the instance. Clear? Instead of creating the function outside a class, assigning it as a class attribute, you know how I could do? I could have created a class like this. Class car def drive of C, right? Print driving C.name. What did I tell you about all definitions at a class body? They create class attributes. So car.drive is a class attribute that refers to a function object. A function object referred by a class attribute running on the instance, right? It's called an instance method. When I say C is equal to car, C.name is equal to Toyota, C.drive, you can see how it works. Is the behavior? Driving Toyota, right? So this is how you create methods. What you normally observe is, instead of putting words like C, people have the convention of using self here. And I tell you that self, though it is highlighted by syntax in most of your syntax highlighting rules, it is not a special keyword. Self is merely a naming convention to indicate the first argument of this particular method is an instance. No difference between a method and a function. What is the difference between a method and a function? Methods are specialized to work on object. Functions are very generic. Give me some input, I will do some math and give you some output. A function is specialized to work on a particular object. That means it knows about the attributes of an object. Such functions, first argument will be reference to that object. Right? And that's how you create this instance methods in this case. Any questions? Doubts about this? Understanding this? You know this. You understood the ABCs of object-orientation in Python. We'll get back after lunch. To get back from lunch, I'll tell you about some more things about these class methods, instance methods, static methods, best practices, all of it. What is Pythonic, what is not Pythonic. I explain all those things. Okay, we'll get back after lunch. Right?